And we are good to go. Did I even put on the mic in the previous class I just had? What's up? It can get so embarrassing, eh? You'd think you have recorded the screen with sound, and you just been recording handwriting. That feeling is very painful. Very painful. When you realize. I just want to check something.
And today we're doing geometry.
Alright. No, it's fine. Got it. Okay. So, the last time we met, we couldn't continue with this class, but we did speak a little bit about voltage, which is potential difference, and electromotive force, which is the force that moves the electrons that flow in a line of current. So there's a reminder here we need to always keep in mind from our grade 10 and 11 work. Ne? So the reminder is that for current to flow, we need an electrical energy source. Ne? So current flows because of an electrical energy source. Ne? Sometimes that electrical energy source is a result of some chemical reaction that produces energy that can be converted into electrical energy, and then we have current flow. Ne? And the other thing we need to also remember is that a closed circuit needs to be in place. So current flows because of an electrical source and a closed circuit. So the importance of a closed circuit, if you think about it, if a circuit is not closed, when you just have the charger connected to the wall and it's not connected to your phone, there's no closing of a circuit there. Or let me just share screen. But true, why is this not allowing me to share screen? Can I just refresh this page? Yeah. Sorry, I just refreshed the window, the tab rather, for learning so that I can access screen share. Yes. So we are here. Ne? Voltage is potential difference, which is the work done per unit charge and to move positive charge from one point, so between points. So I'll just circle that there. That's the potential difference. And it's measured in volts, which is connected in parallel in a circuit. All right. Then current flows because of the presence of an electrical energy source and a closed circuit, and also the direction of conventional current. Do you know what the word convention means? Hey, Magdalene. Magdalene.
Sure.
Do you know what the word conventional means? Okay, convention. Let's just look up the definition quickly. So define convention. The definition of convention, meaning according to the dictionary Merriam-Webster, is a general, it's an agreement or contract, right? So another meaning is an agreement between countries or states for regulation of matters affecting them all, or a compact between opposing commanders, especially concerning prisoner exchange or armistice. So this is in military terms. Or a general agreement about basic principles and procedures. Ne? So when we have a circuit, let's say there is a cell there and it's a closed circuit, and then there is a resistor. The battery will be there, and current would be assumed to flow in that direction. So that is what we mean by convention, to say in the scientific community, the current is agreed to flow in that particular direction, right? And this, of course, is called direct current. So circuits that we normally work with in school, these are part of what we call direct current. Ne? Direct current. So what I just explained is this and that. Ne? So it's from one terminal of the cell, positive to negative. So it's agreed upon that in circuits, current flows from the positive terminal all the way around through resistors back to the negative terminal. That is why when you open up the remote, your battery will have positive and negative. Ne? Or any other device which has a battery, and then that will be positive and that will be negative. Yeah. So that's to show that convention, or even your car battery. You must ask your dad to show you the positive terminal on the car battery and the negative terminal. So your car battery would look something, it's a cube, it's a rectangular prism shape, right? And it's got different cells made up of sulfuric acid cells. So inside the cells, there are sulfuric acid components. That's why battery acid is considered to be dangerous and corrosive. So just ask your dad to show you the positive and negative on the battery of the car. Or have you seen that when maybe he's jumping the cable? Have you seen that before? Hey, Magdalene. You have? Yeah, good. So you'll know that the red color is for positive and the black color is for negative. Ne? So that's the long and short of the convention. Again, we have potential difference. It's work done per unit charge, which is W over Q, and that is simply the voltage. And this is also a form of energy. Right? And then current or electric current would be I, which is the amount of charge passing through a point per unit time, and this is measured in amperes, ne? So it's coulombs per second, which is amperes. And then we also have resistance, which is in ohms, and it is simply the voltage divided by current, and yeah, it's measured in ohms. So it is a measure of how much a conductor opposes flow of charge passing through it. Right, and there are several factors that affect it. Let's just make that slide there. So there are several factors influencing the resistance of a conductor, of a wire conductor. So factors that affect resistance, these include how long a conductor is, so the longer it is, the more resistance. The longer a conductor, the higher its resistance. The higher the resistance. And then there is also diameter or thickness. So let's just put the thickness. The thicker a conductor, the higher the resistance. Or rather, the thinner a resistor. Yes, the thinner a conductor. Yes. The higher the resistance. Yes, the higher the resistance. And then there's another factor, temperature. Oh, let me yeah. So temperature. Higher temperatures mean higher resistances. Higher temperatures, high resistance. And then there's also type of material, right? So the type of material, so tungsten, which is in a light bulb or some light bulbs. This is the symbol on the periodic table. A higher resistance. And copper will have lower resistance. But they are both conductors, ne? All right. Then I believe there is the discussion of Ohm's law, which is quite crucial, but it's also now revision in our part because we did it. Remember, this is now content as it will be summarized in your grade 12 work. So I'm just sharing this with you so you are aware and prepared. In Ohm's law, we discuss the mathematical formula which illustrates that the potential difference divided by the current gives us the resistance. So in other words, the potential difference is directly proportional to the resistance. So increase in voltage or potential difference equals increase in resistance at a constant temperature. So it's important that the temperature is constant, does not change. And also increase increase in current, or rather, let me not say that because I'm not sure what the condition is. We'll have to refer it, but I don't want to be jumping between books. Yeah. But what we do know is that a conductor that has a resistance of 1 ohm means that it will have 1 volt divided by 1 amp of current that flows through it. Right? And then there are specific differences between series and parallel connections that we must know. But when we do know them, which I guess we can always refer to, our previous videos. I guess for the purpose of YouTube videos like I'm sharing now, the link will be added in the description. But the last time we met, we discussed a little bit about internal resistance. And we spoke about when we have, so let's say here, these are the boundaries of the switch. So in the green instance, the switch is closed. And in the blue instance, the switch is open. Right? And when the switch is open, if we have a voltmeter, then the reading on the voltmeter would be 12.5 volts as the electromotive force that is in the battery. So this means that the battery will transfer 12.5 joules of energy for every 1 coulomb of charge. And when the switch is closed, the voltmeter reads the potential difference of the external circuit. So inside the dotted line, this is the internal circuit. But outside of it, we'll have the external circuit. Internal, meaning it's internal to the battery. It's internal to the battery. Now, internal resistance is found inside a battery or cell. And it's a small amount of energy used up inside of it, right? So small. Wait, what? Oh. Why? Okay, your question is why? Why what? Are you still asking the question?
I never heard it from wireless.
Oh, okay. All right, that's fine. So the internal resistance is a small amount of energy used up in the cell. All right. if we had an ideal cell, then the internal resistance would be 0 ohms. And the volts used inside the cell are called loss volts. Alright, so now we get to the electromotive force, right? So let me just do the next slide, like that. So electromotive force, EMF, which is given that symbol epsilon, right? So EMF of a cell is the electrical potential difference across the terminals of a cell while no current flows. So in other words, this is the potential difference across terminals, ne? While there is no current flow. Ne? And then secondly, it is the total amount of electric energy supplied by the cell per coulomb charge. Per coulomb of charge. And then again, it's measured with a voltmeter connected in parallel over a cell or battery when there's no flow of current. So it's still measured the same as voltage in any case across a resistor, but this time it's measured across terminals, or rather over. Of a cell or battery when no current flows, ne? In a circuit. And we would see this in this kind of circuit. We have a resistor there, open switch, and you would have that connected like that, right? Now, how it's calculated? EMF. So since resistance equals voltage divided by current according to Ohm's law, then voltage also equals current times resistance. But if EMF equals the voltage plus, ask.
More sentence we are mentioned what terminals key measured over.
Yes, measured over terminals.
Of the cell or battery when
no current flows
okay.
in a circuit. Yes. As kiska handwriting yaga shaita. Oof. I'll have to write neater. All right. So if the electromotive force is the sum of the voltage measurements, the voltage throughout the circuit, and the voltage, the electromotive force in the battery, potential difference rather in the battery, then EMF also equals the current in the circuit times the total resistance in the external circuit plus the total current times the resistance inside the battery, which is simply I into big R times small r. And that is the electromotive force. All right. And then that summary we discussed for our grade 11 work, where we discussed ohmic versus non-ohmic conductors. It has to do with the temperature change over time as current flows through the resistor. And in an ohmic conductor, we have the following category. So Ohm's law, obey or not obey. Ne? So ohmic resistors, they obey, but non-ohmic resistors do not obey. But this is specific to when voltage or current is varied, ne? When current or voltage are varied. All right. Did you get disconnected?
Network.
I understand. So then the graph of voltage versus current in ohmic resistors, it will look something like this. It's direct proportionality, V on the y-axis, I on the x-axis. Whereas for non-ohmic resistors, it curves like that, right? So here V equals, the gradient so V over I equals resistance, but here V over I does not equal resistance, ne? And then examples that we can think of. In here, it's circuit resistors. And nichrome wire. Let's see, what is nichrome wire or nichrome wire? Chrome wire. Let's see. Oh. Okay. Let me show you what nichrome or nichrome wire is. I don't know how the pronunciation goes, but I want to show you what nichrome wire looks like, ne? So I'm going to share that screen. Let's share something else. Isn't that fun? let's share something else. All right, so here they say it's a family of alloys of nickel and chromium. So nickel is on the periodic table, as well as chromium. It's also on the periodic table. And an alloy is a combination of one or more types of metals. And that's one way of adjusting the properties of another metal so that it can have different properties. For example, wa bona poto ele ya 3 foot madikotwana le bitsa enga speed. E bitsa enga speed madikotwana. Ke madikotwana. 3 foot pot e bitsa enga speed. Poto maotwana. Lina lona last pedi same letter la go ba le lentswe la poto. What is it called? Maotwana fast. Oh, so pija maotwana fast. It's fine. Ka Sotho se nna ke se tlwaetseng re bitsa madikotwana, ne? So madikotwana is an alloy of iron, and I think it's mixed madikotwana.
Okay.
Yeah, that's Sotho, Free State and Lesotho. So again, madikotwana, and it's, I think, iron mixed with carbon so that it forms cast iron. Yes, I believe that's what happens. But now, iron on its own would be a ductile or a metal that you can stretch to a point where it breaks apart. But with madikotwana, it's not ductile. Instead of being ductile, it's brittle. So in other words, potwele ha ka emelela godimo ga roof wa e laser onto a concrete floor, it would shatter or get glass. You know that most. That's why le maoto a gona kgona go ngathela. Ne? So when it's like that, it means it's brittle, but that's because the iron Fe would be mixed with carbon to make cast iron. But that's called an alloy. An alloy. It's a mixture of two types of metals or more types of metals. Mabidi koloi, for an example, they would have aluminum and something else. But aluminum on its own, I think we can dirabo aluminum foil. Or the mafestere aluminum. Abzana stylish amans. So nichrome is a family of alloys of nickel and chromium that's commonly used as a resistance wire in heating elements like toasters, electric kettles, and space heaters. And funny enough, in some dental restorations and in a few other applications. Okay. So in dental restorations, so like let's say lino le salela la bola, ne? Then ga ya dentisting ba fitla ba epa mokoti ole and then ba le faga filling. So that's a dental restoration. It's typically made of nichrome. Okay. And then you have different properties, jawali, different mixtures of nickel and chromium according to different proportionalities. And then that also affects the density, the physical properties of, so like I said, two or more metals, and that will change the properties of the substance. Ne? And then, back to sharing our class. Here, ohmic versus non-ohmic. Yes, that's where we were. All right. And then non-ohmic conductors, ke di light bulb. Tungsten wire, so light bulbs with tungsten wire. Diodes and transistors, ne? So diodes and transistors are really the basis of many electronic components, including phones, laptops or computers, etc. But when you decide to study electronic engineering, you will learn more about those. Then we've got electric energy. Alright, so electric energy is transferred from moving charges to the particles in the resistor. Transferred from moving charges to particles in the resistor. Two particles in a resistor. The particles in the resistor gain kinetic energy. They gain kinetic energy, and the temperature of the resistor increases as the kinetic energy of the particles increases. Kinetic energy, or rather, let's start with temperature. So temperature of the resistor increases with kinetic energy increase of particles. And I think we do discuss that in one of our videos, so I'll just put that in the description. Now, there are a few formulas that we must note here for energy, electrical energy. And it's that work done equals energy transferred, ne? So work done is the same as energy transfer. And this simply means W equals E, and the units for that are joules. So work done would be potential difference times the charge, which is potential difference times current times time, and this equals I squared R times T, which also equals V squared T over R. Now this is when we substitute R equals V over I into either of these two formulae, and then it gives us that. Now just a few definitions. This here is work. This here is voltage or potential difference. Q is charge. I is our current. R is our resistance. And T is time. in seconds, this is in ohms, this is in amps, this is in volts, and this is in coulomb. Work is measured in joules. And then we have another definition, which is that of power. And power is simply the rate at which work is done or energy is transferred, right? And this is P equals W over change in time, which is voltage times current, which is I squared R, which is V squared over R. And this is power measured in watts. This is time in seconds. And we did this quite extensively in grade 11, so now we're just revising. This is potential difference. In volts. This here is current in amperes, and here we've got resistance in ohms. Yep. So from this discussion, we look at the brightness of light bulbs. Ne? So and I think that's like the last thing before we start doing an example and some activities. Yeah. All right. So the brightness of a light bulb. The brightness of light bulbs. So this is determined by the rate at which energy is transformed in the bulb. Ne? So rate of transforming energy in the bulb. By the power P. Not Mr. P, power P. Or maybe I should call my name Mr. Power P. From now on. Maybe not. All right. So as the power increases, the brightness increases. So increase in power equals increase in brightness. So that means power is directly proportional to resistance. Ne? So power is directly proportional to resistance. And this is in series. But now in parallel, the power is directly proportional to the inverse of the resistance. So increase in power equals increase in brightness when a resistance decreases. All right. So, but this is only in light bulbs with a filament, ne? Or a wire. All right. And that's because compact fluorescent lights, they come in a range of power or wattages, but they'll simply blow up if overpowered by a significant increase in voltage or amperage. Right. So we will quickly do an example and then we call it a day, or rather we call it a night because it's 7:30. So this example is to show you how you will get asked these types of questions in the setting of a grade 12 exam type question for electric circuits, right? So the circuit that we are given is as follows. We have a cell or a battery made up of cells, and it has potential difference of 24 volts. An ammeter is connected there in series. A resistor is also connected there, and it has a resistance reading of 8 ohms. We have an open switch. A voltmeter connected in parallel. Right. Ding, 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 ding. And then our circuit is complete. Not closed, complete. So the first voltmeter measures the voltage across this circuit, and okay, we'll put S there for switch, not the energy drink, a switch for a switch in our circuit. This resistor is 3 ohms, this one is 9 ohms, this one is 18 ohms. And a voltmeter, the second one, is connected over there. All right. So the electromotive force is 24 volts and the internal resistance is 2 ohms. Okay, good. All right, and yeah. So we're gonna look at when the switch is closed, open. So in the case where the switch is open switch, we are asked what the reading on V1 is and what the reading on V2 is. So when the switch is open, it means there's no current flowing. Do you agree? Magdalene? When the switch is open, it means there's no current flowing. Do you agree?
Yeah.
Yeah, because current will probably and then not go anywhere. So what would be the reading on voltmeter? What do you think will be the reading? Just take a guess. It's fine if you take a guess.
Eh?
You can take a guess.
You have V1.
Yeah, I have V1. What would the reading be? What do you think it will be? Any guess is fine. The correct one will celebrate. Incorrect one will correct.
Maybe around, let me see.
Remember V1 is voltmeter, Remember V1 is a voltmeter and it measures voltage, potential difference.
Okay.
Yeah. What do you think it will be? Okay, take your time.
Okay. I think maybe it could be yeah 24 week because I wanna do my
Okay.
I think so.
That's correct because the voltmeter V1 is indeed connected across the terminals of the battery, so that would be correct.
Okay.
Yeah, so you're 100% correct. And then V2, what do you think it will be? Remember, our switch is open,
Okay. I think, and it's funny, I think Dolikani.
You think Dolikan? I think they will not Jilikan, they will not be equal. That's because it's fine. Remember that discussion where we can think of the parallel circuit as having an equivalent resistance. Remember that discussion?
Yeah.
Where we can think of this as having an equivalent resistance. So that would mean this is one resistor, two resistor in series, but now our circuit is not closed, so there's no current flow, so that would not have a reading. That's what the question is asking. But good for you for trying, for guessing. we can get to the next part now.
Oh, okay. It was this. All right. Okay.
Yeah. We can get to the next part. So now the switch is closed. So we must find the total resistance in the circuit. Again, like I said, we'll have to find the equivalent resistance of the parallel circuit, isn't it? And how do we add the resistance of a parallel circuit? We say it's 1 over R parallel equals 1 over R parallel 1 plus 1 over R parallel 2 plus 1 over R parallel 3. So the first one is 3, or rather 1 over 3. The second one is 1 over 9. The third one is 1 over 18. And our lowest common denominator is 18 squared. So 3 goes 6 times into 18. 6 times 1 is 6. 9 goes twice into 18. 2 times 1 is 2. And 18 goes once into 18. And 18 times 1 is 18. Therefore, we will have 18, and this equals 6 plus 2 plus 1 would be 9. So R parallel times 9 ohms. Therefore, the total resistance of the parallel component would be 18 divided by 9, which is 2 ohms. Therefore, R total would be 8 ohms plus 2 ohms, which is 10 ohms. And oh no, this is not the total resistance. This is the external resistance. Yes. Therefore, total resistance would be the external resistance plus the internal resistance. And this is 10 ohms plus 2 ohms. Therefore, the total resistance is 12 ohms. Why one? All right. Well done for spotting it. Then the second part, we must calculate the current that flows through the 8 ohm resistor. Ne? So the 8 ohm resistor is connected in series. Ne? So it's connected in series. Therefore, we're going to have to take the total resistance, and that equals the total potential difference divided by the current. Then we do multiplicative inverses. Therefore, the total current will equal the total potential difference divided by the total resistance. And that is 24 volts divided by the total resistance is 12 ohms. And that is simply 2 amperes. And then lastly, we must find the charge that flows past a cross section of the 8 ohm resistor in 1 minute. Not 1 minute, in 1 minute or 60 seconds. Right? So total charge passing through 8 ohm resistor in 1 minute, not 1 minute, in 1 minute or 60 seconds would be I equals Q over delta T. Remember that formula? Then Q would be I times delta T. We know the current is 2 amperes and we know the time is 1 minute or 60 seconds. All right. And this will be 120 coulomb. So 120 coulomb of charge passed through the 8 ohm resistor. So we'll finish off here for the night. I'm tired, but I want to find out from you, because I think I still have some energy where I can answer some questions that you might have. Any questions?
No, I don't have any questions.
Do not have any questions. It's fine. Just to sum up the electricity and electric circuits part of physics, I think next week Tuesday we will just do these examples and then we close it, so that next week Thursday we will do electrodynamics. I think that will be a very important part of physics that we can touch upon, and I think it is exciting and I think you'll like it. So yeah, I'll see you next week Tuesday. Thank you for attending for today.